Okay, so now I'm going to discuss a nice theorem, a theorem that we're going to use for the remainder of the course through a lot of examples. And it's the following theorem, that if we have two angles, alpha and beta, and we have 2 points A and B, and we want to do a rotation about A by an angle of alpha, and followed by a rotation about B by an angle of beta, that this will be a rotation about some point C by an angle of alpha plus beta. So a product of two rotations gives me a rotation where the amount I'm rotating by, the angle, is the sum of the two angles of the two rotations we started with. Now this is true provided that alpha plus beta is not an integer multiple of 2 pi. So if alpha plus beta is an integer multiple of 2 pi, then we want this product to be a translation. So that's something we also have to prove, that it ends up being a translation. So just to be clear, what I mean by the sum of the angles being an integer multiple of 2 pi is that the sum is either 0, 2 pi, 4 pi, 6 pi, so on. Or it could be negative. If alpha and beta are negative, you could have a minus 2 pi and minus 4 pi. So whatever the sum is, if it's a multiple of 2 pi, an integer multiple of 2 pi, then the product of rotations will be a translation. But typically, we have that the product of two rotations, you're not going to have this usually being a multiple of 2 pi. And so typically, you're going to have just take the sum of the two angles here, and this will be a rotation about some point C. So as an example to see this in action here, I'm doing a rotation about this point first by an angle of 40 degrees. So I'm going to imagine rotating all these points about this point by 40 degrees. And keep in mind, it's a counterclockwise, so we're going in this way 40 degrees. So that is the rotation by 40 degrees. Now I want to follow this by another rotation, so I'm going to go ahead and take another point here, this black point, and rotate these same points I just did. Now they're here. I'm going to rotate them by 30 degrees, so I'm going to rotate them counterclockwise 30 degrees. Okay, so the points started out down here. We rotated them 40 degrees around this point, and then followed that with a rotation about this point by 30 degrees. And we apparently ended up here. Now what the theorem is saying is that instead of doing that double rotation, I can do just one rotation by 70 degrees. And it's at some point. That's not really given in the theorem. But we'll see how to get that point in different problems. So there's going to be some point where if I rotate these points, they end up here. And I want to rotate by 70 degrees. So let me show you where that point is. So I'm going to rotate these points now around this one point by 70 degrees. So you can see they ended up in exactly the same spot. So a double rotation is the same thing as a single rotation. And you just add the angles up to figure out how much you want to rotate by for the one point. Again, that works provided that the sum is not a multiple of 2 pi or 360 degrees. Well, I have this option to do over. Here, we'll just do it quickly. So rotation by 40 degrees, followed by a rotation by 30 degrees, is the same as a rotation about some point by 70 degrees. So that's the 70-degree rotation. Okay, so let's go ahead and move forward. This was the theorem again. And let me go ahead and explain the theorem a little bit more by doing the previous problem that we did as an example, which was this problem, which again came from a quiz. This was a product of two rotations, one about A by pi halves, where A is 1, 3, and the other one about B by pi, where B is minus 1, 1. So I did this example in another lecture, and to remind you of the results, we got that f of 3, 0 was minus 6, minus 3. And we got that this fixed point x naught y naught here that takes x naught y naught to itself by these rotations is the point minus 3, 3. So what is the theorem telling us? The theorem is telling us that the product of these two rotations, let's see, add the angles, pi halves and pi is 3 pi over 2. That's not 2 pi times an integer. So the product of these two rotations should be a rotation about some point by 3 pi over 2. So let me give that point a name. Let's call it C. So this should be a rotation about some point C by 3 pi over 2. So imagine you have a point C in the plane, and we're rotating about C by 3 pi over 2. So we're taking all the points in plane, just turning them around this point C. And if you're imagining that, you'll realize there's only one point that doesn't move, one point that stays fixed, and that's the point C itself. If you rotate all the points around C, C's not going to move, but every other point will. So since we know this is a rotation about some point C by 3 pi over 2 from the theorem, it has to be the point that's fixed by F. So it has to be this minus 3, 3. So when we did this computation earlier, we were actually finding that C, that minus 3, 3, which is the center of the rotation for the product of these two rotations. So in the end, the product of these two rotations has to be a rotation about the point C, minus 3, 3, by 3 pi over 2. So to illustrate that, we went through this in our example before. We had the 2 points that are giving us the centers of our rotations in these products. This is 1, 1, 3 here. And we have the minus 1, 1 here. And we looked at what happens to 3, 0. So just to remind you quickly, we first rotate about this point by pi halves. And then we rotate about this point minus 1, 1 by pi. And that took us to the point minus 6, minus 3. Now we just said that this should be the rotation about minus 3, 3 by 3 pi over 2. So let's see where minus 3, 3 is. Minus 3, 3, that puts us right here. And let's look at this picture a little closer here. So I want to rotate about this point by 3 pi over 2. So this should be 3 pi over 2 because we're going counterclockwise. You can see that does look like a 90-degree angle. That looks like pi halves, so this will be 3 pi over 2. So rotating about this point by 3 pi over 2, starting with this point, takes this point to this point. And so the double rotation we did is going to be the same thing as a single rotation about this point by 3 pi over 2. Now, what's important here is to realize is that this is not just about 3, 0. I take any point in the plane, any point at all, and rotate about this point by pi halves and then this point by pi. It's going to be the same thing as rotating about this point by 3 pi over 2. So we didn't have to start with 3, 0. We could have done any point, and it's going to work the same. So that ends this lecture.